And this will be a session, 3 sessions in total, about atmospheric correction and atmospheric radiative transfer and what happens to the radiance in the atmosphere. So it's maybe a little bit more physical than the other lessons or lectures, but it's kind of the basic of the radiative transfer of imaging spectroscopy. So I think it's quite fundamental that you understand at least the major effects, what happens to your radiation when going through the atmosphere. So that's the major goal. And first, to introduce myself, I'm Daniel Schläpfer. I'm partially teaching physics here at a high school, and partially I'm having a company which is developing software mainly for atmospheric correction and imaging spectroscopy data processing. So that's I was at university for quite a long time before. I'm going to start some presentation again. Maybe in between I will interrupt and do some things on the whiteboard, but let's start with the presentation first. The thing is recorded by Yasmin. We'll see how we will get access to the recorded session later. So here you are. So it's about okay. So today I want to mainly focus on the radiometric radiative background of the imaging spectroscopy and on trace gases. Next week, so it will be some quantities, some definitions, and maybe how you get to gas retrievals using imaging spectroscopy mainly. Next, the effects of aerosols, and the last session will be about atmospheric correction and atmospheric compensation routines. So that's the schedule. First, about some introductory slides. So, yeah, well, of course, you should get an overview and do the interaction of the radiation with the land surface and the atmosphere at the same time. And you should get kind of an overview of remote sensing systems. Well, that's a very short section now. So first of all, what's the effect of the atmosphere? If looking outside, specifically now in November, you may see things like that, like smoggy situations. This morning it was quite rainy, and well, radiation looks very different in November than in summertime. And this is mostly due to the atmospheric components and mainly aerosols and well, water droplets at this time. And all of them have the specific effect. Here in this slide, you'd see the effects of the aerosols at the same time with the effect of the gases in the blue sky, some very scattering effects. What's hardly visible by the naked eye is the effect of the gases or the absorption by gases. This is a more specific or more spectroscopic effect rather than an easily visible effect. So that's what we have in daily in our daily view. And you know about aerosols, about the importance of aerosols, I guess, from other lectures in geography. And you know about the plumes of aerosols. Here it's also from some plumes of aerosols from I think from some fires as well. So that's quite a lot of research going on about atmospheric aerosols. This is from a GEOS project. And if you look at the satellite systems available, there are various systems specifically for trace gases and some of them for aerosols as well. So there were in Europe, there were the OMI and Schiamaci sensors, which were able to measure some gases at very high quality, and they using the UV-Vis spectral range. I assume that you know the ranges of the spectrum for remote sensing. This is an advanced lecture, so you should know that the UV-Vis is below 700 nanometers, near infrared, that's between 1 micron and 2.5 micron wavelength, thermal infrared in the 10 micron range, and microwave somewhere else, much further back in the spectrum. And in the UV, there is specifically the nitrogen and sulfur oxides. They got some specific signatures which can be used to track them. There are other gases as well. The list is not complete here. So nowadays one has some more gases. I don't know by mind. One would have to look up because the list is quite long. And so in the meantime, just a few years ago, the TROPOMI mission has been launched, which is able to measure all these gases together. That's a European mission, which will be also related to the Sentinel systems. So Sentinel-5 will be the final gas satellite, which will measure all gases as possible of the atmosphere. Of course, the funding was easier than formerly because of climate research. It's very important to get all the gases right worldwide. So this is in the UV-Vis. In the near infrared, TROPOMI applies to both, by the way. You will see the CH4 and CO2. So the major climate gases. So this can be detected in the near infrared. As well as in the thermal infrared, you will get the emission of these gases as well. There are other sensors, don't go through all of them. The thermal, they measure the emission of the gases, so by their temperature. If you measure the emission, you get the advantage that you can measure it all the time, also at night. So you get a better daily resolution. Then we get the microwave, where you get some absorption, also some emissions, passive microwave emissions from water vapor, for instance. They are mainly used in meteorology as well. Then if using the multispectral imagers, like the standard remote sensing instruments, you can always get the aerosol optical depth, AOD, that's aerosol optical depth. And even polarization of aerosols, if you have multi-angular observations, and the kind of the idea of the aerosol size distribution by the angstrom coefficient can be measured by multispectral imagers just from the spectrum with about a few bands. That's already feasible. So these are, they're also part of the game. So if you want to know about the state of the atmosphere, usually one combines a few of these sensors, and then one gets a good image. Nowadays, one has quite a good overview of what's happening in the atmosphere. Usually it's at a low resolution. So usually this is at a 1 kilometer or a few hundred meters resolution, and not at the resolution we're used to in remote sensing. If we go now to, so here you see the, for instance, the NO2 distribution worldwide by Schiamaci. That same can be done by TROPOMI nowadays. And you see these hotspots of nitrogen oxide that's from combustion mainly in Europe and in China. And well, as I said, it's the low resolution, but you get a very good overview. And the same for methane. Here one has a certain problem. As you see, you can't get it over water. You saw before that methane is visible or is detected in the near infrared, and water does absorb all the near infrared. So that's why you can't get any information back from by absorption over water. So that's it's just dark there. But over land, you can get a nice distribution of methane. And for the water, for the precipitable water, this is emission image of the water worldwide from IIS, and that's a thermal image. So in the infrared or thermal infrared measured. So these are used in remote sensing. Also, the standard meteorological satellites have such sensors on board to measure the water, the emission mainly, not by absorption, but by the emission. So if you go, what we have, why do we still care about the gases in imaging spectroscopy? Well, at first, with those sensors, we don't have the option to go to high resolution spatially. So we are talking about 1 meter resolution range in imaging spectroscopy rather than a few hundred meters. So we could do large high resolution mapping, for instance, over cities of certain gases. That's an advantage if you go for imaging spectroscopy. And the other thing is, the main goal here is about atmospheric compensation. So if you want to compensate for the effects, you also need to know where they are or where the gases are. And that's why it makes sense to measure it directly with the imaging spectroscopy sensors. So much for the introduction. Short interrupt. Any question for now? If not, then I'll go into some background, some radiometry at first. And there are some quantities to remember. And some of these quantities should be well known to you already. So you should know about transmittance, absorbance, emittance, reflectance, what it is. You also should know the radiometric quantity or distinguish between irradiance, solar flux, and radiance. And maybe some easy calculations should be feasible for you if you get from irradiance to radiance. Would be strange, but still, anybody never heard about these terms? I don't know how the base lectures are, but from my knowledge, they should already have been explained earlier. But it's kind of a repetition. But maybe it's always not good to hear things 2 or 3 times until you start understanding it. So first, about the spectroscopic quantities. So if doing imaging spectroscopy, one first has to define the x-axis of the spectrum. So what to put on the x-axis. And in optical remote sensing, we're usually using the wavelength. Wavelength being measured in nanometers or in microns. In spectroscopy, we use nanometers mainly, whereas in multispectral remote sensing, one rather uses the micrometer. A lambda is used as a symbol. The wavelength range, as I said, from the UV to the shortwave infrared. The wavelength is a strange unit, you will see afterwards, because if you think about the radiation or how the energy is defined in radiation, it's mainly related to the frequency. The frequency defines of a photon by h times the frequency being the energy of a photon. So the frequency defines the radiation. So that's why one should use frequency, but we don't use. So in microwave remote sensing, they are the only ones using the frequency as an x-axis reference. They use the hertz. And the symbol often an F, sometimes a little nu, that's not a V, that's a nu. Which is used for the frequency, depending on literature. So that's both are used. So don't get confused if once they got a nu and once they got an F. And the last reference, you can use the wave number. That's and this reference is used in spectroscopy. Wave number being 1 over the wavelength. That's 1 over lambda, written down here. This nu is the wave number, not the frequency. By accident, they use the same symbol, which is again confusing. So if you see a nu, check if it's the wave number or if it's the frequency. So in this case, it's the wave number, but it's 1 over the wavelength, and they're using the inverse centimeter as a unit there. That's from the old chemistry units like grams and centimeters instead of meters and kilograms. And the one thing which is strange about the nu and the wavelength is it's not directly related to the frequency. So you can divide the frequency by the speed of light, but then you got the index of refraction is coming into the game. So the wavelength changes if you're in a different index of refraction. So if you're going through the atmosphere, this doesn't make a big change, but still you get maybe one on the third digit, you get a difference. So because the index of refraction of air is about 1.001, you get this difference of wavelength if compared to the vacuum. It's of course, if you do underwater remote sensing, you have to be very careful because underwater you get a different speed of light and your wavelength changes significantly, and you will don't see the same wavelength anymore but you still have the same frequency. So whenever you see wavelength, check out in what medium you are. We had this problem formerly when calibrating systems. So you calibrate against the wavelength. If you calibrate them in the lab, you're at air pressure of 1000 millibar, and you have got a certain density of air, you get a certain index of refraction. Now you put the same sensor in a satellite or in a high-flying aircraft, and the index of refraction is different there. And so the whole wavelength shifts. And this shift makes about 0.1 or 0.2 nanometers. So it's visible in the data. And we only learned this a few years ago that we have to shift the wavelength a little bit due to the index of refraction of air. So that's relevant in imaging spectroscopy. That's what I want to say. So these are the three base units. Yeah. Question about that? Just start talking if you got questions. And I think you don't know if one can raise hands here, but yeah, I'd see, I guess. Now about the optical properties of matter. There are these base quantities we're using in remote sensing. Usually if doing remote sensing, one wants to have the reflectance as an output. So that's the rho. Sometimes a big R is used for reflectance factor, or rho for reflectance, the difference. I'll come back to this later. And for the transmittance, a big T is often used, or a little tau as for how much radiance is going through something. Absorbance, a little a alpha, and emittance is how much is emitted, which portion. All of them are unitless. So they don't have a unit. That's just relations between incoming and outcoming radiation. That's usually defined between 0 and 1. Can be between 0 and 100% as well, or can be also in some cases even be more than 1. This happens if the path is changing, or if there is something shifting, some fluorescence happening, some shift in energy from one wavelength to another or so. So these are the quantities. And now you have to be careful. This is the absorptance, the absorption coefficient. So it tells how much is absorbed. If you look into what chemistry people are using, they're using the term absorbance and not absorptance, big A. And this is a logarithmic thing. So they take a logarithm because if you increase the concentration at some point, you don't get much more absorptance. And so it's an exponential thing. At first, you get very lot of effect. And if you put more and more of stuff in a solution, it doesn't help a lot anymore. And the logarithm is a better way to describe this effect. And so that's why in chemistry, they will always use this term. It's a logarithm of 10 of the transmittance. And also another confusing term is the term albedo. Albedo, also an alpha is used. Albedo is related to reflectance and not to absorptance. And but in you know, albedo from energy balance models in physical geography, very important parameter. We are using it. We don't. I avoid using alpha for it. I'm just talking about rho, an integral of the rho, or an average of rho over an area, such that you don't have a confusion with the absorbance. And last one, in aerosol science, we talk about optical thickness. And maybe at that point, let's give you an example how they compare to each other. And I'll do it this way. I'll go to the y. Okay, I got to close. Oh, let's stop share. Then I'll go here and go to the whiteboard. And so, first of all, just repeating what I just said. So if you got a certain block and you're entering with a radiation into it, so three things can happen. Of course, something can get reflected. So this is the reflection. Something can get absorbed, alpha, that's inside, and something can get transmitted, that's tau. So this is, that's why you, if this is the irradiance I, that's why all of the three of them should sum up to one, because it's energy conservation. What's coming in has to go somewhere. So that's why rho plus alpha plus tau equals 1. That's the normal thing. And now if the whole thing is in equilibrium, what's absorbed in here needs also to go somewhere. So either the whole thing warms up, so it's getting the energy inside, or it's emitted again. So if it's emitted, then you get an epsilon, emittance coefficient. And if you think about it, if it's in equilibrium, as much as it is absorbed should also be emitted. So that's why the emission coefficient is usually the same as the absorption coefficient. So if you get a 100% absorbing thing, then you also got it's also a 100% emitting. So 100% absorbing alpha, 100%. You talk about the black body, and black body is, for instance, the sun is black because it's absorbing everything and it's emitting almost perfectly. So it's strange. It's a black body because it's fully emitting its energy. And other black bodies, well, it would be a completely black hole, and whatever is fully absorbing and emitting at the same time in an equilibrium. So this is about these quantities to repeat. And the second thing is, let's see, this makes is the I'm always saying the relation between transmittance and the other two quantities. So if you got, for instance, a transmittance of 10%. So just assume you got 10% transmitting medium, so only 10% of the radiation is getting through something. Then you get T equals 0.1. So you usually don't write it as percentage. And now what would the chemistry guy say about that? He would say, well, you got an absorbance which is minus the log 10 of the transmittance, and this is of 10 to the power of minus 1. That's 0.1. And that's minus 1. So, and this will be 1. So the absorbance in that case is 1. If you got if you go to T equals 0.001, so 0.01, then you get an absorbance of minus log 10 of 10 to the power of minus 2, then you get 2. So that's how you change the units. And for at the same time, if you talk about the aerosol guy, he would say, well, I'm interested in the optical depth only, or the optical thickness. And optical thickness is also a logarithmic thing. It's for the same reason as the chemistry guide talks about it. So it's T. I also use an asterisk for to say it's the optical thickness. And this is minus ln of T. And in that case, it would be 2.3. And in that case, it would be the optical thickness minus ln of T 4.6. So that's how the numbers compare for the same quantity, but written by various scientists. So just to give you an example. Okay, I can stop sharing that. It's just something. Go back, sharing the question about that. So let's go. Go back to the presentation. There it is. So that's something I just explained on the whiteboard. Now going to the irradiance term. Irradiance is what's coming in, and so you look at a certain area, and that's why you just check a square meter and how what energy is arriving there. Energy as well, it's the power what you use, because it's continuous flow. Doesn't make sense to talk about energy. It's much more sensible to use the power unit. So the energy per time or per square meter. And because we're talking about spectroscopy, we also split it up in the wavelength. So we use the watts per square meter and nanometer as a standard unit for the irradiance. So how much energy per square meter is coming in per nanometer. Of course, if you have a broadband, it maybe micron would be a better idea, the micrometers instead of nanometers, but we are using nanometers. And now we start at the irradiance at the at the sun. The sun is emitting something, and it's emitting it in all directions. So also from the edges you get something, and from the middle you get something from the solar disk, if this was the solar disk. By the way, do you see the arrow? I hope so. And it's going to within a degree, 0.5 degree variation, it's approaching Earth. So this means, in fact, it's so in fact the whole thing is much more narrow. Yeah, so the 0.5 degree, that's within a very short range of angle. So it's so the two rays are almost parallel to each other. So and this means if they're parallel, if you do the modeling on Earth, we have to think in parallel irradiance situations. So don't draw the sun like that. So if you draw it, it's quite slow here. So if you draw a sun with the air, okay. People always think the rays are spreading with distance, and this is not the case in the range of remote sensing. So within these few kilometers above Earth's surface, we don't have to take care of the spreading of the radiation because we are very within this 0.5 degrees. So that's just to think about. So, and what's arriving at the Earth's surface, or the irradiance at the outside of the atmosphere, we talked top of atmosphere irradiance or solar irradiance basics. We call this E0 or E sun, which is just given by the distance to the from Earth to Sun and by the emittance of the Earth itself. That's given by this equation to the left. So the radiant power is just how much watt the Sun emits, and then you have to divide it by the distance, then you get your Earth irradiance. This, of course, is variable over the year. You may remember from geography at what point you get the highest radiation. The highest radiation is question. At what, in which season you get the highest radiation from the Sun? Easy geography question. Nobody dares to say. There are so many people in here. Okay, no interactions feasible. So at which date do you get the highest radiation? Remember aphel, perihale situations, and it's the aphel is in winter time. So in February, you get the highest radiation from the Sun, and it makes a difference of a few percent. So it's relevant if you do the modeling. So that's the point. So let's go to the Sun. The Sun is variable, it's not very stable. This is not an optical image, that's a magnetic image, but anyhow, it just shows how variable the Sun may be. You got this burst and this continuous movement on the Sun, and it's very hard to get the stable information about the Sun itself. And if you remember this 11-year cycle of the Sun, so it changes every few years, the irradiance, and it changes within 2 watts per square meter within the solar cycle. We are using an average of that because 2 watts is below 1% variation, and whatever is below 1% variation in radiometry is neglected usually. So that's something I'm talking about radiometry. And one claims that radiometry is the least accurate measurement theory you get in physics or in radiometry. You're very lucky if you get a 1% accuracy. So if you go better than 1%, then you get in problems with the photon counting and the photon statistics. So you can't easily get better than 1%. That's why the 2% or these 2 watts, which is 0.2% roughly, is neglected. One takes an average of the solar irradiation. Another thing is the spectrum changes as well. And the spectrum changes, first, this slide is about the variations measured from various devices. So if you compare various measurement devices, you see all of them tell something different. So whenever you put a new device on a satellite to measure the Sun, you get a new data set, and this new data set usually differs from the older one you had. And nobody knows really which one is the true one, and how much did the Sun change in the meantime, and what happened. So it's very hard to get the Sun right. The same you see if you look at the spectrum. So here we compared just 2 measured spectra of the Sun, an older one from 1997 to one measured in modeled in 2011. And if you compare those in the level of an imaging spectrometer, you get differences which are well above 1%. So here you get up to 5% difference in spectrum, and the same happens also to other references. So when you start modeling the spectroscopy, you have to be aware that you're easily getting more significant errors, specifically below 5 microns, so below 0.5 microns. So that's if you look at spectra later, you have to be aware if you see a problem at 0.43, for instance, it may be the solar spectrum and not the atmosphere. What else do we have? The solar irradiance is, well, here's the solar irradiance extraterrestrial curve at the top and on the ground. In between something happens. For instance, you're getting some absorption here by gases. Like the water vapor, which is absorbing 900, 1130, also further up. And like oxygen, which is very strongly visible, usually at 760. That's the very significant peak of oxygen, which you see in all imaging spectrometers. These are the two major gases. There are more gases which are very less obvious. Specifically at one further back at 2 microns, you get some methane and CO2 as well. Moreover, you get these sharp absorptions at low wavelengths. These sharp absorptions can be some nitrogen, but most of them are so-called Fraunhofer lines. So these are the lines from the sun atmosphere, not from the Earth atmosphere. That's why you see them already in the extraterrestrial solar irradiance or top of atmosphere solar irradiance. So here we got this absorption in the UV, and which was visible, of course, also on the ground. So all these small spikes here, that's a natural spectrum. That's not an artifact. And now where is the maximum of the whole irradiance? There is this Wiener relation, maybe you remember this law, which tells us that if you got an emitting body of a certain temperature, you're getting you can easily measure the maximum of this, or you find the maximum wavelength of this emitting body, which is given by this relation to the temperature. So if you take the temperature, for instance, of the sun, which is maybe let's see if I can write that. If the sun is 5,700 Kelvin, that's the sun, Kelvin. Okay, what's the wavelength? The maximum wavelength you get from the sun would be 5,700 divided by, or the other way around, 2,900 divided by 5,700, roughly 0.5. So the maximum wavelength is 0.5 microns. That's why we're getting this maximum around 0.5 microns. If you look at that curve, it's not exactly at 0.5, but this is already some absorption happening from the sun here. So if you do the fitting of a Planck curve, of a continuous curve, you get a maximum at about 500 nanometers. That's the maximum of the sun and of the Earth. You look into this later. If you're on the ground, it looks a little different. On the ground, the maximum shifts. We are at about 600, 550 to 600. That's due to the absorption by aerosols. Aerosols reduce the radiation in the short wavelengths, and that's why you get the shifted radiation with maximum at about 600. And plants use this 600 range for chlorophyll absorption, so they use the range of maximum absorption to get the energy, as much energy as possible out of the radiation. So that's the on the ground maximum. And talking about the solar flux, this was the irradiance. The solar flux is a little bit different to the solar radiation. Solar flux is given by what you get really on the ground. So what you get on a flat ground, even if you got a tilt of phi, that's the incidence angle, solar incidence angle, or it could be the solar zenith angle if it's a flat horizontal surface. And you're getting into it. Here you would have A0 is here, sorry, is, so that's A0 here. That's this thing here. That's the area which is normally used. But if you go to the area down here, this area is A0 divided by the cosine of phi. So A0 divided by cosine phi is the area down here. And if you compare the two, the irradiance A0 times E0 times A0 to the ground irradiance, so EG times the area down here, they should be the same because it's energy conservation within that beam. And so that's how you get to the so-called cosine law. So if you find the ground irradiance from this relation up here, you see that it's E0 times the downward transmittance, tau downward, times the cosine of the incidence angle. And so the irradiance per square meter decreases with the cosine of the incidence angle. So that's said in a complicated way why you're getting darker pixels on a sloped surface. So it's just a decrease by the cosine of the incidence. That's how much less energy you're getting. It doesn't talk yet about the properties of the surface. It's only about the irradiance effect. We call this quantity a solar flux. It's a strange term because fluxes are usually defined differently in physics, but in this case, they just also use the solar flux quantity, which is again watts per square meter nanometer, but now it's a real surface and not a surface perpendicular to the radiation. This one was perpendicular to the irradiance. So that's about the definition of solar flux. The ground solar flux, you can even think about what else happens on this square meter. You got the direct solar flux, e.g. direct, and you got some diffuse solar flux or diffuse irradiance on the surface. And you also could get some terrain irradiance from the side. And so you got to add up all of them to see how much energy is reaching the ground. And now we are on the ground. We got a irradiance, but we are measuring the radiance. So we are using a sensor so with a certain opening angle, measuring on a pixel on the ground. And we have all this irradiance stuff. And we got some reflectance on the ground itself. So we got to multiply the irradiance by the reflectance, multiplication of reflectance times irradiance. And we got to divide by the observation angle. The omega, sometimes a big one, I'll see the difference will be shown afterwards. So that's the solid angle under which you observe the pixel. And that's how it's defined, the radiance. So you get it per steradian. I'll just come to this later. And in the Lambertian case, this steradian reduces to a pi. So the easy calculation to get the radiance from irradiance is just you multiply the isotropic reflectance by the irradiance and divide by pi, then you get the radiance in watts per square meter steradian nanometer. So that's how you get to the radiance. About the solid angle, so this T omega, some are not familiar with that. That's why a little explanation. Omega is usually the area divided by the radius squared. So on a sphere, so it's spherical. So it's like the radian. Everybody knows the radian. Radian is 2 pi for a whole circle, like the circumference. And for a sphere, you got if you look at the whole sphere and you got a radius of 1, then you get a total area of 4 pi because the area of a sphere is 4 pi r squared. So that's how you define it. So the steradian of a whole sphere is 4 pi. The steradian of a hemisphere is 2 pi. And if you look back at that, if you want to get the radiance, you use only 1 pi. And that's one thing which is happening. If you look from the side here, then you're getting less area. Maybe I should explain this afterwards on the whiteboard, but time is already approaching for the break. But it's just you get a 1 pi relation for the radiance, even though the solid angle is 2 pi for a hemisphere. That's because of the projection or the cosine law of the radiance. And if you talk about the omega on a pixel, then this one reduces by the cosine that's really something I think I got shortly to show before the break, and afterwards we'll go into the break. Jetzt rein nicht mehr. Oh, okay. No, I think we go into a break right now. I have to switch something here. Okay. We're gonna explain a little bit more about these relations of on a surface, because it was a little bit in a rush before. So what's the radiance? It's again about radiance, and you think about a certain area. Let's say it's 1 square meter. This one gets irradiated by EG, ground irradiance. So you get a watts per square meter, nanometer as a irradiance, and now you observe it. If you observe it, then you observe it over a certain angle. And this angle is, we use a big omega in remote in spectroscopy or in angular research for this solid angle in steradian. And the reason for that is, if you go to the side and observe the same angle, the same area, like from here, you see what happens. This angle gets smaller. So because we are relating the radiance to the irradiance, we always have to take the same square meter. So we can't just enlarge the square meter. So this means that the so-called projected projected solar angle, solid angle is the angle at nadir, which is omega r equals omega r at nadir is omega, the other way around, is omega r equals omega r times cosine phi again. So that's again a cosine law. That's a cosine law of observation. And then on the other hand, we got a cosine law of irradiance. And the two of them may cancel each other in certain situations. For instance, if you look at something bright from the side with a constant omega r, so if you look at the other way around, then so if you'd take, maybe like do it that way, if you have a certain solid angle and you look at the same surface from the side with the same solid angle, you get a larger surface on the ground. So you increase the area at the same time as you decrease the amount per unit area of radiance. So that's why in this case you see the same brightness. So if you look at certain objects from the side, it doesn't seem to get darker if you look from the side. That's because of this effect. In the same field of view, you're getting more surface at the same time. So in the same cell of your eye, you get you get more surface. So you cancel the effect of the decreased irradiance or decreased radiance. But that's what I want to explain again. That's the reason now that's the reason that you're getting a pi if you integrate over the whole thing. So if you integrate this thing over the whole hemisphere, then you get a pi for the whole angle, because it's decreasing to the side. If it wouldn't decrease, it was a 2 pi, but if it's decreasing to the side with the cosine, you've got to integrate the cosine over the hemisphere and you get a pi. And that's why rho equals L over pi times E0. So you got to divide by pi if you want to get the the other way around, sorry, pi, this way. That's pi times L over E0, then you get the reflectance. Okay, now let's go to the reflectance again. That's also something maybe I'm just drawing it. So if you now observe a certain object, it has a certain reflectance, and you know the reflectance is variable with direction. So you heard about BRDF maybe earlier, and well, BRDF is just incidence, observation. You got 2 angles or 4 angles, and for every configuration of incidence and observation angle, you're getting a certain BRDF, bidirectional reflectance distribution function, or a certain reflectance, and the function is the thing which may be variable over the hemisphere instead of being constant. So typically it's getting darker if you look from the side, or it's getting if you get some specular reflection, you're getting more. Or you get if you get a hot spot, or if you look with the sun, you get more reflectance. If you got less small shading within the object, so that's the BRDF effect. That's bidirectional. So it's incidence and observation. So incidence and observation. And now if looking at our targets, we have some additional terms to be considered. You will see in the presentation afterwards, which is if you look at it in a conical way. So if you have an observation with a cone, which is normal, conical, maybe I should have taken different color for that. So that's the conical. Then you see it may be variable within the cone as well. So that's typical if you do a ground measurement with a spectrometer, you have a conical situation. From a satellite, the cone has a very small angle, and that's why one can consider this being directional, because it doesn't make a difference in the model if you do a modeling within the cone or not. That's a conical thing. And then the last thing is the hemispherical thing. If you got the whole hemisphere and you get from everywhere the same radiation, we're talking about the hemispherical situation. It can also be talked geometrically wise, but in radiometry, hemispherical means you get everywhere the same on the hemisphere. This is only the case in remote sensing. You've got a white sky situation, so completely clouded sky, then you should get almost the same from every direction. And this is the hemispherical irradiance then. The hemispherical observation is hardly feasible. Then you'd have to integrate over the whole hemisphere. So that's for the introduction to this. A short, let's switch back to the presentation. And going back to the presentation, let's share this. Okay, I think you got it now. Yeah. So I introduced these terms before. So we got the bidirectional, BRDF, HDRF. I don't go in detail through that because it's not the main topic in this lecture. It could be a whole lecture by itself talking about bidirectional reflectance distributions. But the more important ones are, for instance, the BHR. That's the one which is of high relevance, because this is the only quantity which is not variable for within an object. So it's bihemispherical reflectance. So we also call it the spectral albedo. So if you have this means you integrate in both directions, and you get one spectrum from one object. So if you want to compare a library spectra to an instrument, then you should have b-hemispherical reflectance quantities, because those are not affected by the RDF. So it may be a goal of atmospheric correction to get b-hemispherical reflectance in the end, or should be a goal. And in remote sensing, we have the hemispherical direction, the HDRF as a normal thing. And this is used in an ambiguous way. So physically, one uses the definition from Nicodemus, which says hemispherical means diffuse irradiance, or isotropic irradiance from all directions. And for practical reasons, some remote sensing scientists are using a definition which tells us, well, you just have a hemispherical irradiance, which is variable somehow, and you should take care of that. Then some people use the same term for this, which is very confusing. But just be careful if using the term HDRF or HCRF. There are two definitions around for that. So a little bit later, come to these questions and exercises. That's up to you. I guess you got a few so you can now try to go into these questions and find out, or try to find your answers to that. And please, I'll give you 5 minutes for this, and come back with questions afterwards. Maybe you have to go back into presentation if you got your presentation downloaded already. Go back into this. Let's see if you. Okay. Going back into that. So what's the difference going into the questions? What's the difference between extraterrestrial ground and solar flux? So that's was the first part. Answers to that. Should I ask somebody? I just see a few guys here. Maybe Manuel Jack is here. Or not. So the difference between extraterrestrial ground and the solar flux is you started out of the atmosphere. Extraterrestrial ground is on the ground, but perpendicular to the direction, and solar flux is on a real square meter on the ground. If it's tilted or not, then you talk about the flux. So these are the three terms. If doing the modeling, we're starting with the solar flux, or we want first to have the solar flux. We're starting with the extraterrestrials already. And one other difference in unit is the steradian. So it's the observation angle. We don't have an observation angle for the irradiance. There we check out the square meter, or we have just a flat surface which is measured. And also in measurement devices, you put out a flat diffuser and measure the energy onto the diffuser. And with in the radiance, you have a field of view, so-called, or you got a pixel, which is a certain field of view, and this has a certain angle. And number 3 was, so number 1 was sphere round, and then it's impossible. And tilted ground. And 2 was the observation angle. And 3 was maximum radiance at 290. If you do the calculation, it's 2,900 divided by 290 or the other way around. So you get 10 microns. So this is the thermal. And 4 it needs a little bit of calculation. But you calculate pi times L divided by E0, and this will be 0.45. So that's the reflectance you're getting. So, and in 5, it's that's the thing I just showed earlier. It's the double effect of the cosine. So if you look from the side, you observe more area, and that's why it doesn't get darker. Okay, questions about those? Okay, then I'll proceed with the presentation because it's now the second part. We have half an hour left, but it's already related to the exercises you're doing afterwards, because in the exercises you should try to find out how to get some signature of atmospheric gases. And yeah, now it works. So you should know about absorption, and you should know about the how to find the absorbing gases from a spectrum. So first of all, if you do absorption, what happens? Well, you get usually in the UV, you get electron transitions within the atom. Molecular absorption means that's the variation of atoms against each other, so vibrations, and also in the bindings of the molecules, some absorption may happen. And if it's going to lower energy, it's more rotations, motions of the molecules which can absorb energy. So that's just a question where the energy is going to. But usually, all these items only can absorb at certain energy quanta or certain energy levels, because only certain states are feasible for molecules. That's why you see absorption lines or absorption bands of gases typically. The Beer-Lambert law is the law which tells us what happens if some radiance gets into a block of gas and how much is transferred into a fluid. I talked about transmittance earlier. You get a path length, so a certain length of the path through which the radiance goes. Here we talk about radiant intensity. One could also use its watts per square meter, the irradiance term here as well. Intensity is just more generic than irradiance. So you start with the initial radiation, which is going through a certain length and absorbed by so-called extinction coefficient. The extinction coefficient is given per meter. So how much is absorbed per meter in this law, and you multiply it with the length, then you get the so-called optical depth, T asterisk. I mentioned this earlier today. And if you take the exponential of that one, then you get the transmittance. Oh, that's why you get the optical depth by the logarithm of the transmittance. That's what I explained earlier. So that's how the transmittance is modeled easily. The only thing you need to know is the extinction coefficient of the gases. And this is a total attenuation. That's how it's defined. So it just tells us how much is lost. It may consist of the so-called absorption coefficient and the scattering coefficient. So these, because attenuation may happen by scattering, and you lose something which is going away. I'll talk about scattering next week. And absorption is just, it's staying in the gas, it's absorbed, and it's maybe a meter later at a different wavelength. And the optical thickness is just the addition of the two times delta L. So the gamma is the addition of the two. And optical thickness or optical depth, they're often used synonymously. Sometimes scientifically it's made, some people may make a difference, but it's not consistent. that it's just this tau asterisk. So much for the definitions. Where do we have absorptions? Well, in the optical spectrum we are looking at, we got the oxygen, which is prominent, and of course the water vapor, but despite the water vapor, we got the oxygen, which has strong absorptions in 680, 760, 1270, which can be seen and which also can be used for calibration, because they're very sharp. Oxygen is a simple molecule, doesn't have a broad variation of absorptions, and that's why you get only sharp absorptions. Carbon dioxide is a little bit more complicated, but broader, and the typical absorptions are in the 2 micron range. So those are visible in the spectrum. The 1601 is hardly visible. Ozone is a weak absorption, but continuous at about 500, 600 nanometer. And methane can be seen at 2370. And so there are some applications with methane and imaging spectrometers. So this is an illustrated view of that, which was once made by Jens Nicke, and which just shows where these absorptions are. Oxygen at 700, and water vapor is almost everywhere. So you can't do anything about water vapor, or you can't do any spectroscopy without dealing with the water vapor. By the way, that's a logarithmic scale. Be careful. So that's it's very low, just to show the small absorbers. But even NOx can be measured with if it's very low absorbing, even though if it's a very low absorbing here. So again, these transmittance curves, you'll see them in the exercises afterwards as well. So if you look at the water vapor, only about 50% of the spectrum is not affected by water vapor. So you have to get rid of it if you want to see the spectrum on the ground. Because of time limitations, you can go into these questions later, and as I didn't see much interaction either, so it's maybe better if you do it yourselves. Yeah, that's just a calculation of optical thickness, which gases, that's shouldn't be too difficult for you to solve now. Now for the gas retrieval, how to get these signatures evaluated, how to find the amount of gas. The normal way is if you look at an absorption feature, so it's absorbing at some wavelengths, and you just want to know how much it's absorbing, and you compare the absorbing area to the surrounding area. I called this the measurement area to the reference area, or measurement bands, spectral bands. And then that's how you can find the absorption depth. And the absorption depth is related to the amount of gases. And that's, if you evaluate this properly, you should get, and you compare it to a simulation, then you should find the appropriate amount of gases. That's possible, but it relies on calibrated data and good modeling of the area. So of the radiation. We call this a differential absorption method. There are two definitions of differential absorption methods, by the way, but this one is in one band only. So you find the transmittance. So you got to find a method to find the transmittance of the gases, and then you have to calibrate the transmittance against the amount of the gases. So you've got to find a model which tells us how much gas makes how much absorption. And then you have a calibration function against which tells us the amount of the gas against the transmittance. And then if you know that, you can of course go into the image and find the transmittance for the whole image and transform it by the calibration function to the total gas amount. That's something you will do in the exercises. So you'll have the transmittances at various gas amounts, and you can find a calibration function and try to do this yourselves later. To find the transmittance, very typical thing is to do a continuum interpolation. So if you have the spectrum, you just do an interpolation of the continuum to the middle of the spectrum, and you compare what's in the middle against what should have been there without absorption. So that's a very common method to get the absorption depth. And the absorption depth, it's implemented in the software you will be using later, so you don't have to calculate it yourself. There is one catch of this, is if you get some additive component, so if you get some scattering or whatever, this will change. So if you add everywhere something, so if you shift the whole function, then you would get a different relative absorption. If you divide this value by that one, and if you divide that value by that one, you get a different number, even though the absorption is the same. So you have to subtract these additive components before doing the transmittance analysis. So that's what I call the atmospheric pre-corrected differential absorption. So you take care of the aerosol scattering first, and then you do the atmospheric gas retrieval. That's a common method in the meantime for in imaging spectroscopy. You could do it in the exercise. You will do it without, and maybe you see some effects of that or some problems with that, or specifically over dark objects. You will get into troubles. Here is an early result of that. What you see as water vapor amount is typically related to the terrain model. At the bottom, you got the terrain model. So the height of the ground, and on top you should see the water vapor. And if you see this relation, you're already quite close to reality. But nevertheless, you have problems over water because very low signals in water. It's often not feasible to have gas retrievals over water. So this is a river up there, and there's a lake here. But that's how you can find the water vapor contents. There are other possibilities. Instead of absorption depth, is modeling the full spectrum, which is in theory the much better way to do it. So the problem is the following. You got the atmospheric gases. So remember this curve, the blue curve, which are atmospheric gases. But at the same time, you usually got liquid water for instance, in leaves in there. And liquid water has an absorption spectrum which overlaps the one of the gases. And also ice and snow, they overlap the one of the gases, specifically at 940 nanometers. So here, and usually this 940 nanometer feature is used for water vapor retrieval. And if you neglect the effects of the liquid water on the other waters, you will get artifacts or inaccuracies. So the idea of Rob Green and also Dave Thompson, they do a fitting of all of that together. So they create lookup tables where all the phases of water are in, and you search the best fitting spectrum in the image, which yields really, really nice results and works quite well for well-calibrated data. We have sometimes a problem at 940 where the fitting is done because detectors often split here. Also often for technical reasons, spectrum is quite bad exactly at this range where you would need it for this technique. So it works with the average sensor, but it doesn't work with Apex or other sensors, this method. And it has, there is another alternative for instead of curve fitting or similar to curve fitting, as you use a smoothness indicator. So smoothness criterion, that's something we're currently developing, and there were some earlier works on that. So instead of taking for the absorption thickness, one starts modeling a few corrections just with variable water vapor, and searches the water vapor amount which renders the smoothest spectrum in the end. So the idea is simply that if you look at this spectrum, it's perfectly unsmooth if you have the water vapor absorption. So there are all these spikes in there. And if you're over a certain range, if you do the correction, right, you should see no variations anymore in a continuum, and or very, very little variations. It's also, the reason is also that you can do that is that natural spectra are not varying in the same way as atmospheric spectra. So in the atmosphere we have these very sharp spikes, and in nature you seldomly see such sharp spikes, specifically up to 1.2 microns. It's a difference in 2 microns range. There you have natural spectra which with sharp absorptions. So there we have a different, it's not feasible there. But in the visible range, it works quite well. So this is another way to do water vapor retrieval. So 3 ways we're currently seeing. So here's a result of the curve fitting techniques where they have now put together vapor, the 3 phases of water together. So melting snow, ice, and liquid water and the water vapor. So they get very nice results. They get one disadvantage currently is computing power, because you do a fitting for every pixel of a very large lookup table. Usually one image takes about a night to process, and if you want to do a whole campaign, you have to wait a few nights. And if compared to differential absorption, it's using this method in an operational fast way is not yet feasible, not yet possible. Even in scientifically, it's the best method available currently. So one always has to think about operationality as well, and not only about scientific best thing. The last method I wanted to mention is the differential, the DOAS method. DOAS is used for the NO2 retrieval at 400 nanometers. And the strange thing is, or the interesting thing is, that NO2 has only very small variations there at 425 to 450 nanometers. It's below 1%, but it's always the same. So, and it's a lot of bands where you got these variations. So you can do this, the statistics over a full range of wavelengths. And you can do, again, kind of a smoothness criterion. It's also this, so you start doing a few corrections. You do a polynomial fit, and you search for the best fitting or least deviating nitrogen amount within this wavelength range. So that's how it's done. You just vary the aerosol amount on the smooth polynomial, or not the aerosol, the nitrogen amount on the nitrogen dioxide amount, yeah, on the smooth spectrum. You modulate with various amounts, and if it fits, and the way if you find the best fitting function between the modeled and the really measured difference, you have the correct amount of NOx. And as you see, it's a very small variation. It's 1 per mil, but you have so many bands that finally it will work. So and also it's a relative thing. It's not absolute. It's no absolute modeling. So it's about relative errors, and relative errors in radiometry are much better than absolute errors. As I mentioned before, absolutely in radiometry, we're talking about percentages, 1 or 2% accuracy, but relatively, of course, we are better off. Relatively, we're in about 10 times better, or 20 times or so. So this can be applied. So there were some nice results over Zurich at high resolution, and it has been repeated over other cities. If you take NOx, you can find the air pollution in cities by this method, which is a very nice application. But of course, you need to fly high resolution imaging spectrometers to get this out. But the same method is also used from satellites for low resolution outputs, and there it's used in an operational way. So, so some final questions here. Now, what wavelengths are best suited for water vapor retrieval? I mentioned them earlier. Maybe you look them up now. And yeah. let's talk about number 1 first. Yeah, 900 nanometer is not bad. If you look at the spectra exactly, it's maybe 950, yeah. Yeah, 940. We're talking about the 940 band, but 950 is also fine. So it's in this range. And maybe others, there should be other bands as well there. Because problem with 940 is that 940 is affected by low responsivity of silicon. So if you have silicon detectors, they get noisy. That's why, yeah, 820 and 1130 are the other 2 bands which can be used. So with cheap spectrometers, we're using the 820 band. So 940 is a kind of a standard. 820 for cheap. I should start those. Spectrometers. Cheap means some of them are even ending at 940, so they don't go further than about 900. And 820 is you got better responsivity of the silicon. And 1130 is for shortwave infrared. And you also use the 1130 and for low water vapor amounts. Because it's strongly absorbing. If it's highly absorbing, the 1130 almost saturates. But if it's low water vapor, it's better to use the 1130 than the 820 if you got the choice. So that's what's the first question. And the other, so the next question would be the additive terms. Well, it's just you can prove this mathematically. If you just say, well, A over B is not the same as if you do it mathematically, A plus C divided by B plus C. So if you add something to both, which is C, which is an additive term, then you don't get the same variation. And if you're calculating a transmittance, you relate you do a simple division by the transmitted to the non-transmitted radiation. And if you add something, the C cannot be cancelled. That's the problem here. That's now the third. Then maybe a question back to you before which are the limitations of absorption depth analysis. As I mentioned, one major limitation. Where do we got in problems if thinking of the images? Well, what surface types are causing troubles? Well, it's exactly, yeah, that's the or water, other surface types. I mentioned, so if you, the curve fitting technique that had the advantage that you take the water of other targets into account. So that's why you'd have problems over water, snow, and humid vegetation. Because there you got a crosstalk to the water in these targets on the ground. This can be solved with the curve fitting technique, but advantage, it's very fast and easy to calculate, relatively easy to calculate. That's why one uses it quite often. Okay.